So in this video, what we will do is we'll continue our discussion towards the direction of implementing contextual embeddings. And we start from where we stopped last time, where we actually built a way to actually do that. If you recall, we had this kind of a simple self-attention mechanism that is actually had this implemented this kind of a very simple kind of a linear equation. And in this kind of discussion, what we will do is we first want to motivate why we need to move away from this kind of linear way of calculating this kind of embeddings, and see exactly where this will lead us. So I will call this kind of a second discussion on the self-attention kind of mechanism, the sort of elaborate, or let me not call it elaborate, let me call it the sort of probabilistic self-attention. At the end of the day, everything is probabilistic, or will end up in some kind of a statistical kind of model. And so that kind of discussion is pretty much aligned to our aim anyway. So first observation I want to highlight is that this X hat that we came up is completely dependent on, and in a kind of a deterministic way, on the context-free embedding vectors that were lumped in X. If you think about it, even A itself is something that is obviously completely dependent on X. And therefore, it definitely would like to sort of start getting into this kind of following discussion. Since this X is something that came from outside of the transformer, how can we actually allow the transformer to actually have some say on this X hat? That's the whole purpose of actually introducing this kind of elaborate kind of mechanism. So I want to kind of motivate that from going back to this kind of sentences and providing some kind of discussion along these lines. So I want to go back to this I love bears. And just want to highlight that the subject in this sentence is obviously I, the verb is love, and the object is bears. In the second sentence, she bears the pain. The subject is she. The verb is bears, and the object is the pain. And to, I know it's a kind of a long discussion, but it's kind of repetitive. The third sentence, bears won the game. We have the subject, bears. We have the verb, won, and the object being the game. So if you think a little bit about, I would like to have the ability to associate into the contextual representation of the token bears, additional kind of to have an impact on that kind of representation from additional kind of factors and then just the surrounding kind of tokens. And for example, you can notice that the object, which I think I used the orange color earlier, this bears here, has this kind of this token bears has a kind of a role of being an object in this kind of a grammatical pattern. And many sentences in English, have this kind of grammatical pattern. They start with a subject, then there is a verb, and then there's an object, and there are many other grammatical patterns that we will need to accommodate anyway in this kind of discussion. In the second sentence, bears is, I think I used, did I use green? Yes, I used green. So bears is over here is associated with a verb. And probably you guessed it, bears over here is associated with a subject. So as we can see, in each of these kind of different kind of contexts, the role that this token is actually playing in this kind of grammatical pattern is different. And this is really one of the ways, one of the reasons why we would like to provide this kind of a more flexible mechanism into, which will end up being a probabilistic mechanism in this kind of a mapping from xi to xi hat. So what I would definitely suggest here is we would like to kind of think about a new kind of embedding kind of space where we have some kind of dimensions here. As you can see from this kind of discussion, the axis, let me call this axis the objectness kind of axis, where the degree of objectness kind of varies along this axis. This, let me call this the verbness axis, and this will be the subjectness. There could be another axis that we have not really seen a grammatical pattern of, which is this adjectiveness axis. And as you can see, you can imagine if you want to sort of map these kind of tokens in this kind of axes, bears, the token bears here in these three different kind of contexts of the discussion, definitely we would like to associate bears to be kind of pointing towards, not exactly aligned to, but kind of pointing towards this kind of objectness kind of axis. And in the second sentence, bears will actually be pointing towards the verbness axis and so on and so on. So we would like now to implement this kind of mechanism, to suggest kind of an implementation. And I want you to imagine that tokens, each token, which I will represent here as a kind of a square, is emitting three types of vectors. The first one, I will call it QI and will stand for query. The second will be the key. And the third one, K, and the third one, V, will be the so-called value. And all of these tokens will actually do the same. So I will refer to, let's say, QJ, KJ, and VJ here for this, let's say, token. So what I'm would like now to associate with the query vector. So let me write it a bit better. The query vector Q is semantically want to associate it with who am I looking for? And by who, I mean another token which carries some kind of role that it is going to help me map myself better into this kind of a dimensional space, in this embedding space. Let's say with key, I'm actually finding, I'm associating semantically with this who I am vector, which is the value, V, will actually play the role of this vector xi that we have just looked at over here. And it's actually there to decouple the two, the simple self-attention mechanism from the vector which is we receive, if you like, at the input. So we'll see that this kind of a value is going to be adjusted by this simple self-attention mechanism. And obviously the more elaborate version of that we'll see kind of shortly. And we would like to implement this kind of decoupling. So we will use this kind of a query and key kind of vectors to calculate effectively the red vector we saw just now. And this red vector will apply to the value vector that we will adjust. Okay, so this is effectively the token, the value of the token itself. And we'll see how this will actually, adjustment will actually be done in this kind of a more elaborate version. So what are these kind of queries, keys, and values as kind of can be discussed now with respect to this kind of a lower dimensional kind of space? And actually plotted here kind of four axes, but you can understand it will be a dimensional space much larger than 4. And the axes also have a kind of semantic information like object, verb, adjective, and subject, but in reality, obviously, it will not have the semantic meaning and meanings. So what it actually will happen here is that this, let's take, for example, the first sentence. The first sentence is bears is an object. And as we discussed, definitely the objects are the object as being an object, it actually points towards the object kind of axis. And it requires help from, let's say, this token, which is love, which so happens to be a verb. And definitely, if we see the love here, let me plot it as a kind of the yellow vector over here. Love reports its identity, claiming that I am a verb, so therefore reports identity via a key. Let's say K love. And this is the K bears. So it kind of wants to, so the K bears says, okay, I'm actually looking to find something that it is a verb. So I believe that I will be qualified better from receiving help from a verb. So it is actually issuing a query key that it is going to look like this now. And therefore, every single token, which is a verb, in this case, love, because the dot product between this kind of query bears and the K love is going to be pretty large. As you can see here, the two vectors are pointing almost in the same kind of direction. Then we are going to effectively have a fairly significant kind of communication between love and bears in this example of a context that we have here in the first sentence. And so if we understood this kind of mechanism, effectively we are building for every query that we have here, we are issuing its token, is building some kind of communication with corresponding kind of keys. It can help this kind of token. So we have, in fact, if I may plot it like this, maybe a bit confusing. I may just want to plot this something like this, that this is in fact a very high communication kind of bandwidth between these kind of tokens. and not so much between this and other tokens. Okay, and so this is the kind of way that I want you to just see this kind of attention kind of mechanism, which is based on this kind of concepts of queries and keys. And what we will actually do now is we will I want to start writing down this kind of dot products again, because the dot product kind of approach is going to be maintained with us, remaining with us. So we will just look at this, what this dot product will replace the original dot product. So I'm going to be effectively forming a Q matrix, which is X times WQ, and a K matrix, which is X times WK, I'm sorry, WK that is, and a V matrix, which is X times WV. And as we discussed, what will happen now, we are going to go from X transpose to a query key transpose. And this query key transpose is going to be written, given this kind of equations, as XWQ times XWK transpose, or XWQ WK transpose X transpose. This is definitely what we call the generalized dot product. So we went from a kind of a simple dot product between the tokens to this kind of generalized form of dot product. And if you were wondering why we have this kind of situation here, what these things are actually doing, these are effectively projections. And we have seen similar things, if not identical things, to concepts such as PCA, or principal component analysis, where we have similar kind of projections done into some kind of dimensional space. So we take the original kind of tokens, X's, right, and we projected them using this kind of projection kind of matrix, WQ, into another space that we called, that is manifesting here with the matrix kind of Q. And this is basically the space where queries are falling, are projected to. And the same thing with keys, and the same thing we'll see with values. We haven't discussed values that much at this moment in time, but in this specific projection kind of space, I just put keys and queries in the same space, just to indicate what is going to happen. During the training kind of process, these communication channels are going to be gradually being built. Initially, there is very little information about what's really the best token it can help me in this type of context of bears being kind of animals. And these channels, communication paths, are going to be built gradually as training progresses. As losses are sort of minimized, we will see this kind of communication channels being kind of formed. And effectively what it means in the vector space is that, as we just saw, the query that I'm issuing for the kind of ith kind of token is going to end up in the neighborhood of all the tokens, of the tokens in the context that it can help it. So effectively, in this kind of a d-dimensional space, we will see something like that being formed in this kind of vector, in terms of vectors. So these are all the tokens that have very high communication channel bandwidth between those tokens and the token that is seeking to find who can actually help it best form its representation. Okay, so I think this is kind of the simplest way of thinking about the keys, queries, and now let's see an example. So let me actually write down first, before we see this kind of example, after training, the projection matrices which are obviously programmable matrices, just like trainable parameters we had in other kind of neural architectures, are going to be the ones that are WQ and WK, are such that next to the query in this d-dimensional space, we'll see the keys that best respond to it as neighbors. Another way of actually also looking at it is do this kind of multiplication explicitly. If I have, let's say, an X matrix that it's consists of x11, x12, x13, x14, we said that our matrix will be the context 3, and the d dimensions are going to be here, x21, x22, x23, x24. And let me write also x3, x34. And we have a W matrix, let's say a WQ matrix, which is W11, W12, W13, W14. Mind you that this matrix WQ is D by D. This is W21, W31, W41, dot, dot, dot. I'm not going to populate this kind of matrix, but you can imagine all the other kind of elements. So if you do this kind of multiplication, Q, which is X WQ, what we actually want to get at is that we are going to get some kind of a, so we have X, which is T by D, and WQ, which is D by D. Therefore, Q will be T by D again. So this will be a Q11, Q12, Q13, Q14, all the way down to Q44. So I think it's interesting to see, to take just one element and make sure that we kind of expand it to see something which is of interest here. So the Q11 is going to be W11, X11, plus W12, X12, plus W13, X13, plus W14, X14. So what we see here is effectively the following. The W matrix is adjusting, is weighting appropriately the features of each token, because this is basically features of token number 1. As we said, the token number 1 is a D by 1 kind of dimensional vector, and effectively the WQ matrix is say, okay, I need this kind of feature, give me some portion of the other feature and so on, put them kind of together to form, if you like, the first element of the projected kind of a query vector and so on and so on. And so we will see that at the end of the day, these query vectors, which are are going to be the rows of this kind of a Q matrix. Its first element of this kind of a query vector for the first token is going to be the Q11, the same way the Q12 will be formed, Q13, Q14, and so this weighting is going to effectively give us this Q bears kind of vector. At the end of the day, whether or not you sort of stop here this kind of discussion, we will continue a little bit more to understand a little bit more about the value. You will end up with exactly the same diagram as we started the discussion. We have some kind of a lower dimensional space, and we now form the values as projections of the original kind of tokens. So we have this kind of VI, and we end up with some kind of VI hat using this kind of elaborate, or we called it probabilistic, attention kind of mechanism. So this probabilistic is now evident why it's called probabilistic, because at the end of the day, we're going to have a training process, and this kind of training process, based on some kind of criteria we will see, will effectively define all our WQs, WKs, and WVs. Okay. So, this is the reason why it's called probabilistic. And now I think it's time to kind of draw an end-to-end kind of block diagram to see a couple of other things that we need to implement this kind of diagram. So we will start with X as this matrix of tokens, which is, as we discussed, T by D. We are going to multiply this with a WQ to form the Q vector, the Q matrix, which is T by D. We are going to do exactly the same thing here for the queries, for the keys, to form the K matrix, which is T by D. And we are going to do the same projection, assuming the similar kind of projection using a WV matrix. And so these two projections are being used to calculate the dot product, which, as we discussed earlier, is forming a scoring kind of matrix, T by T. We are not going to change, obviously, the softmax, but before the softmax, we need to explain why we have this kind of scaling done. And now it's a time to have, just before the scaling, this softmax that is going to create the attention weights, which is T by T. And these attention weights are going to be used to adjust using this kind of multiplication, which I kind of didn't write very well here. This multiplication between the projected tokens on the value space to form effectively with this multiplication the so-called value hat, which is A times V is equal to V hat. So this A is T by T, V is T by D, and V hat is therefore T by D. As we expect, we started with a T by D matrix, X, and we'll end up with a V hat matrix. And so one of the things that we would like to kind of explain now is this kind of division by 1 over square root of d. And this can be kind of well understood if we look at the course site, because we have an example over here. And this example is discussed in this kind of a section. So the scaling kind of discussion, and actually you can see when we divide this course by 1 over d, what we achieve. So what we effectively is happening here is you do not want your attention weights to be very sparse. And if effectively they are very sparse, then this means that you are not going, sparse means that there are lots of elements which are 0. This means that you're not going to be receiving a much help from those tokens. We want to get, softmax is going to normalize things out for us anyway. So, and therefore implement this kind of competitive situation between tokens, because if you assign a very large weight from one token, you're going to have to adjust downwards the weights of other tokens. And therefore, softmax, in order to do its job properly, is going to effectively need to see some kind of a non-sparse kind of view of this kind of tokens in its input. So every token is kind of divided by 1 over square root of d. And this is basically the end result. Here in this bottom right corner, you will see the situation where we have sparsity. We do not want that. And by this kind of division, we are achieving the upper right quadrant here for the same input vector that we see here. Okay, so this is basically the reason why we have this kind of division. And you can actually see the code. This is the reason why sometimes we refer to as scaled dot product attention, this method. Okay, so this was the situation where we have now the vectors, the so-called single head self-attention, and we call it kind of single head because we are going to have an extension to that in terms of multi-head. But if you understand the single head self-attention, the multi-head self-attention mechanism is kind of a straightforward. So what is really the problem that this multi-head self-attention is now needs to solve that single head is not able to? Well, if you go back to that specific kind of construction, what we have seen here in this kind of example with this kind of 3 sentences, definitely we have seen one linguistic pattern where this linguistic pattern is kind of a subject, verb, and object. And definitely we have many. For example, if I give you the sentence, let's say, we went through bear country. So this bear here is definitely, as a token, takes the semantics of an adjective, and therefore it may, I know it's a kind of a limiting example, but we definitely have a plethora of ways where in various kind of languages we just cannot have just one sort of linguistic patterns. We have to accommodate multiple. And so the reason why we actually would like to introduce kind of multi-heads self-attention, where a head is the block diagram that actually you see here, is exactly that. We would like to provide an opportunity to find other relationships that are not going to be necessarily limited to just one. So here we saw a relationship that governs, grammatical relationship between verbs, objects, adjectives, and things like that. But obviously there may be other relationships as well that we would like to highlight. So What I'm going to do now is I'm going to draw a block that I'm going to call the so-called single head self-attention. So this diagram here, I'm going to call the single head self-attention. And I'm going to suggest that we may want to investigate multiple relationships between the tokens. And I'm going to lump everything that you have drawn just now into just a single block. What we're going to do next is we're going to concatenate the values, the VHATs, and pass the output through a WO. It's not a 0, it's an O, W output matrix. I usually call this matrix kind of a mixing matrix because it is mixing together the various kind of head results into one output will actually be at the end of the day D by D. Now let me stop here because we have a kind of a diagram that kind of warrants some kind of an explanation on this kind of multi-head self-attention. And let me call, before I stop, this H to be the number of heads. So we have here 3 heads. And in another kind of video, kind of expand on this and actually start dealing with the last stage of the transformer, which is basically the raw computational kind of stage as well. So I'll see you in another subsequent kind of video.